The sun's energy powers almost all life on Earth. And that energy comes from nuclear fusion. If we could mimic this reaction here on Earth, we could produce a virtually limitless supply of clean energy. In the south of France, a project under construction could be our best hope of achieving the power of the sun and stars here on Earth. This is ITER, initially an acronym for International Thermonuclear Experimental Reactor, but also Latin for the way. We're back for a second visit to see how far down the way to a clean energy future we have come. As unscientifically as you can, please explain what's going on here.
We are building an international lab, trying to find out the scientific and technological feasibility to use fusion to generate power. We are not making a power plant here, but we are making a laboratory, trying to explore the possibilities. And currently, we are in the phase of assembly and construction of a tokamak. The tokamak is a big reactor for fusion. And globally, the scientists and engineers believe that the tokamak is the best achievable approach for power generation through fusion.
What seems to me even more miraculous than the high-level physics you're doing here is that you've got people from 35 different countries collaborating on this amazing project.
Yes, we need a kind of diversity. We need all kinds of expertise globally. The cultural differences is difficult, but actually important, very, very important side to have this, all the different countries to join this and bring the expertise. So it's great.
I'm in the main corridor here at ITER, and it's got an interesting feature here on the wall, which shows how long this project has been running. In 1985, Ronald Reagan and Mikhail Gorbachev agreed to develop fusion energy as an inexhaustible source of energy for the future benefit of all mankind. 1988, conceptual design activities began. 1992, engineering design activities launched. 2001, ITER design approved, site studies and ITER agreement negotiations began. 2003, China and Korea joined ITER. In 2006, the Chinese tokamak East experimental advanced superconducting tokamak achieves first plasma. And in 2006, the signature of the ITER agreement. It's been running for a very long time. Razor last visited ITER back in 2020. Then the main buildings were in place, but the tokamak pit and the assembly hall were completely empty, awaiting components. Well, it may be one of the world's biggest scientific experiments, but it's also an industrial site under construction. So it's time for the safety gear. But while I get into that, why don't we remind ourselves exactly how nuclear fusion works?
About 100 years ago, we discovered that the source of light and heat in the universe, the most common energy source in the entire world, is fusion. What we're trying to do here is we take a giant donut-shaped vessel and we inject it with just a few grams of two forms of hydrogen, deuterium, which has an extra neutron, and tritium, which has two extra neutrons, into this gigantic 800 cubic meter donut. And then we run electricity through it. When you run electricity through certain gases, you split the electrons from the nuclei, so you have a charged plasma. Because charged particles are subject to magnets. So we put magnets out around, we put magnets sort of this way around the donut, and we put a big magnet in the middle. So we have created now a plasma inside the steel cage, an invisible magnetic cage that can hold these particles in place. Now we're going to heat it, and we're going to heat it to about 10 times the temperature of the sun. No material on Earth can withstand that, 150 million degrees. No material can do that. So the cage, the steel cage, is bounded by this invisible magnetic cage. And through doing that, we get to a point where so many fusion reactions occur that we're getting, our goal at ITER is to get about 10 times the energy out of the plasma that we put in as heating into the plasma. So that's really the goal of ITER. We call that a burning plasma, a self-heating plasma. Remember we said deuterium, tritium going in. What comes out is a helium nucleus and a neutron. The neutron is the only uncharged particle, which is very cool because that will escape the magnetic field and it will hit the steel wall, the magnetic metal wall of the tokamak, of this donut. And in hitting that wall, it's just like if you shot a bullet into a steel plate. The kinetic energy, if you felt the plate afterward, it would be hot. The kinetic energy turns to heat. And the goal is to extract that heat, which not at ITER, but in commercial machines, would produce electricity.
We're starting at the assembly hall, the biggest building on site, and at this stage, also the busiest. Kirsten Haupt is our guide.
Somebody's opened us the gates, that's very nice.
It's a big site. To get from one place to the other, driving is sometimes necessary, and the lovely Kirsten is making sure we get to our next appointment.
We are coming now to a place that I like to call the Times Square.
Central to everything.
It is indeed, that's why.
Which way do we head?
We are going through the gates here.
Okay. Heading towards the assembly hall. It's quite hard to explain, you know. I don't know if the camera will have given you the real idea, but this place is huge. It's the biggest structure I've ever been in. It's absolutely mind-boggling. Epic is the only word, on this epic scale. It's really, really astounding.
We are now in the assembly hall.
Yes.
So here, all the big components that have been manufactured, they're coming in here and being assembled into modules or pre-prepared for the movement into the tokamak pit. The center stage here is taken up by two big tools. We call them the subsector assembly tools. That's for the modules of the vacuum vessel. Vacuum vessel consists of the 9 parts, and each of those sectors is being assembled with 2 D-shaped magnets and the thermal shield in between. And you actually see from here vacuum vessel sectors inside. You can see them inside.
So you mean this big grey thing is the assembly?
They are actually 2 if you look closely. So you see...
Always something happening at ITER. So what is this piece?
Well, that's actually a handling frame, that's what we call it, for one of the thermal shields that go around the vacuum vessel sector. This one is for the inside of the thermal shield. So if you imagine the D, on the straight line of the D, this is where the thermal shield is going to be, one part of them. We have 3 altogether, and this is for the handling of them.
So this is just built to handle one of the components?
Yes, it's basically a tool, a framing tool, yes.
In fact, there are over 100 specially designed and built assembly tools because ITER is a very complicated puzzle. The core of the tokamak is made up of 9 vacuum vessel sectors, each with 2 toroidal field coil magnets attached and a layer of thermal shielding in between. These 9 sectors are put together using the sub-sector assembly tools before being lifted and lowered into the tokamak pit. 3 of these sectors were put in place in 2022, but during routine testing, 2 defects were found. The first relates to the thermal shield, which is the shiny silver covering we can see on the flat side of the sector in front of us. The cooling pipes welded onto the surface will eventually contain liquid helium to cool the superconducting magnet system. Professor Sergio Orlandi is head of plant installation and machine assembly.
If you see in that portion below, you see there is the thermal shield. That's which has the silver coating. In that sector, you can see the external pipe has some rust, but very localized, not that you can see. We have discovered doing the vacuum test, because only with ice was not so easy to discover them.
On testing, it was found that stress corrosion cracks up to 2.2 millimeters deep had developed in the pipes. This was caused by the bending and welding of the pipes, compounded by a slow chemical reaction due to the presence of chlorine residues used in the welding process. Like everything at ITER, the solution will happen on a grand scale.
We are thinking to remove this piping totally, to make a calibration of 3-4 millimeters to remove this thickness. And in this way, we export all the sources generated by stress corrosion cracking. And this way, we can proceed with the new installation of new piping, produce the new stitch welding, and will not be performed any more coating, as well as cleaning with chlorides, because we eliminate the root cause.
Once the 9 vacuum vessel sectors are lowered into place, the plan is for them to be welded together. And this is where the second problem was found. If we look up here, there's the inside of the vessel that will finally house the plasma, or at least a part of it. And this is one of the pieces that's going to be needing repair. The edge of the sectors had irregularities where they meet, meaning they could not be lined up precisely enough for automatic welding.
It's not a defect because there is a big error, but there is a defect in order that we can move into the pit and automatic welding, which means that we don't do manual welding, which in general has the characteristic or the defects not to be repeatable. While for automatic welding, you can assure the quality in perfect manner because you have to calibrate the machine as a function of the configuration of the sectors.
Perfect welds are needed because the inside of the tokamak must be a vacuum to prevent heat transfer from the superheated plasma to the sides of the vessel. It's 2 grams of hydrogen isotopes that are going into there, and we need something this huge to contain the plasma that 2 grams creates.
Yeah, it is really mind-boggling if you consider the space. The plasma volume in there is going to be 800 cubic meters, but the volume of the chamber altogether is 1400. So by that you already see that the plasma cannot touch the walls. I mean, there is still space outside the plasma, but indeed there are only going to be 2 grams of fuel in there at any given time.
The first plasma experiments were planned to start in 2025. However, this will now be delayed. You've only been in the job 12 days, but you've already got a couple of very big problems to solve, haven't you?
The delays because in many cases we are making the first of a kind components. By no means we can do it right once. Probably we need to gather experiences and trying to guide later generations of reactors.
This experiment is going to teach you how to build the power plants of the future, not just your successes, but your challenges as well.
Before we talk about tokamaks, they are smaller, they are experimental, they are lab devices, they are not really reactors. This one is the real reactor. So if this is succeed, and we have no doubt that we can very quickly to build the next generation.
While there's been media speculation about the costs and delays caused by the defects, Professor Orlandi doesn't believe it's too much of a setback. What does that mean for the timeline for when you establish the first plasma?
I'm happy if I'm capable to do. My target is to enter into the second half of the year 2024. So we have achieved the target to repair everything within 18 months. But in the meantime, we have decided to produce additional value, like to go out of fission rules.
Professor Orlandi is referring to the fact that only days before our visit, the Nuclear Regulatory Commission announced that fusion energy would now come under the same rules as particle accelerators. Previously, construction at ITER was governed by the rules that apply to fission reactors, which break apart uranium or plutonium. But fusion is overall a lot safer, as there is no chance of a runaway reaction. So it's believed this will help speed up construction going forward. Construction of the world's largest fusion experiment, ITER, continues, getting components ready and building the surrounding infrastructure. The scale of the project is hard to understand, and so are some of the amazing technical achievements that will happen here, such as the temperature of the plasma inside the tokamak reactor. I always struggle with this. You're talking about the inside of that vacuum, inside the magnetic field. How can anything on Earth be 100 million degrees?
So when you're talking about a vacuum and you have a limited 2 grams, 3 grams of hydrogen in there, what you're really talking is about particle velocity. And what you want in particles, as we all learned in secondary school physics, you know, when you boil water, we learned that the particles in the water are moving faster. In a solid, they slow down somewhat. They're still moving, but they slow down. So if you're getting to a plasma, this fourth state of matter, you want to get to a velocity where 2 positively charged particles no longer repel, where they will actually be going so fast that they just run right into each other and fuse. So it is the velocity of the particles that is determining that temperature equivalent.
At the other end of the temperature scale are the superconducting magnets. To be superconducting, they must be cold. Sui Jian runs the cryogenics plant, which is now complete and undergoing testing. Tell me exactly what we're seeing up here.
We have 3 set helium cryo plants.
Yes. Cryo meaning cold.
Yes, minus 270 Celsius degree.
In fact, the liquid helium that cools the superconducting magnets will be 268.9 degrees Celsius below zero, or 4.2 degrees on the Kelvin temperature scale. To put that into perspective, 0 degrees Kelvin is as cold as it is possible to get in the universe.
At that temperature, only liquid helium is available, so that's the reason we use liquid helium.
Well, shall we go and have a look?
Okay, let's go. Come in, please.
Oh my goodness. Every time I come into a building here, I'm just blown away by the size. And this isn't even one of the really huge buildings, is it?
Yes. And this building is building 52, and we call it cryo plant. So we have 3 set helium cryo plant.
Let's go and
1,
have a
2,
look.
3. Yes.
So this is going to be filled with liquid helium?
Yes. At the west side of this building, we have several tanks with storage all the gas helium inside, and we have compressor station to compress all the helium gas to here, and here we have 3 cryo plants. It can produce high pressure liquid helium will supply for the tokamak superconducting magnets, and will be returned to the compressor station and will be arrived here, then reproduced into liquid helium provided again.
It's on a constant cycle.
Yes.
Let's just head over here, just to give our viewers some scale. 1, 2, 3 of these, when they're filled, that's going to be a lot of helium.
Yes, you're right.
It's enormous. The huge cryo plant will be cooling the largest superconducting magnet system in the world. One part of the system are the colloidal field coils, 4 of which are being built on site.
So from here you see really the size and the scale of the magnets.
So how many of these magnets will there be?
So there are 6 colloidal field magnets. 4 were manufactured on site.
Why did you build them here on site?
Because these 4, the size is so big that they cannot be transported.
When my colleague Shini Samara visited in 2020, we could see the magnets more clearly because they were under construction. What are they made of?
So these coils, their core, they are made of a stainless steel jacket where you have the superconductor inside it.
Yeah.
Right? And then we just wind it.
Yeah.
And then basically this is the coil. And we have to build also the electrical joints. And then you have to apply also all the insulation and also some resin that you need to put all around the coil to make it like one solid body.
So what is the actual superconducting part made of?
So the superconductor is made of, for these coils, of niobium titanium.
Okay, I know what titanium is, but what's niobium?
is also a chemical element, and the combination of both makes this a superconductor.
The 6 colloidal field coil magnets are responsible for the shape and stability of the plasma. Superconducting magnets are able to carry higher current and produce stronger magnetic fields than conventional counterparts. They also consume less power and are therefore cheaper to operate. But what's going on over here?
Yeah, so there we are preparing to do the cold test of the colloidal field coil number 4.
A coil test, what's that mean?
So here we will cool down the coil to 80 Kelvin, mainly to test its mechanical and electrical integrity when you cool it down. So when you cool it down, all the things tend to shrink. So we are going to test if we have some components that could break during this mechanical contraction. So this is a cryostat. A cryostat is basically a vacuum chamber. Okay, first we do the vacuum, we do a leak test on the coil to check the integrity of the circuits. And very important also here we do very critical electrical tests.
So the electrical test is just to make sure that at these low temperatures it is going to do what it's supposed to, create that enormous magnetic field that can contain the plasma.
That's it. And one last thing is that I have to say we're going to apply for the World Guinness Records for the biggest coil manufactured up to date, which nowadays the record is with CERN, and we're going to apply for it, because according to our calculations, our coils are bigger.
Bigger in size or bigger in power?
In size.
Oh, yes. Great. Well, I hope you win that record. Everywhere we went on site, there were people from different countries working together. For example, the tokamak assembly contract was awarded to a Chinese construction team. They've just started work assembling the central solenoid, which is the backbone of ITER's magnet system. 13 metres tall and 4 metres wide, it's made up of 6 independent coil packs that were built in the US. How many people do you have here from China working on this project?
It depends on the workload. In the peak time, we have more than 100 workers, about 50 or 60 management team, including engineers and designers.
The magnets themselves were built in the United States, but your consortium has been hired to assemble it.
Exactly. It's not only a simple assembly, but also some, there will be some R&D for this assembly, for the special process. Since this kind of superconducting is the first of a kind, you may know the name of ITER. It's an experimental reactor. So there are a lot of R&D activities on site for the installation. It's not only just a simple, assembly, put something together or weld them together.
Don't worry, I didn't think it was simple. The last stop on our visit is what our guide Kirsten refers to as the cathedral, the tokamak pit. Li Chin Chow is head of coil power.
I will show you the biggest tokamak devices in the world. Okay.
Oh my goodness.
Okay.
Is my mind going to be blown again? Oh yes, it is. Oh my goodness. We've been talking about the tokamak for 2 days, and that is the beginning of the building of the tokamak.
Yes. Yet at present, we have the Sector 7 installed in this
Have a look,
pit.
Benji. Turn around and have a look. That is the... Remember we saw it in the construction hall?
Yeah.
This is now in place where it will eventually create a plasma. I can see the containment vessel here.
Yes, vacuum vessel, yes, you're right.
And then here is one of the great big magnets.
Yes, this is the TF coil outside the vacuum vessel.
What are we seeing down here? Are we seeing magnets down here at all?
Yes, colloidal field 5 coil. Totally, we will have 6 colloidal field coil.
Yes.
Okay, this position is PF5.
Okay.
A little higher, maybe that position, we will have a PF4.
Right.
And just that position, we will have a PF3, PF2, and a PF1. It's at the top of the tokamak devices.
Now tell me something else. So in that D-shaped instrument, the plasma will be sitting where? About halfway?
First, start from the central of the vacuum vessel.
Yes.
Okay, the central line of the vacuum vessel.
And in the middle of that plasma, it will be how hot?
Okay, the nominal design of the plasma of ITER in the operation situation, that will be 150 million degrees.
And then on the outside...
It's very amazing.
It is. It's just... I can't even get it in my head. But on the outside here, where I can see this huge magnet, how cold will it be?
Okay, it's around 4K, you know.
So the temperature of the middle of a star to the depths of deep space in what? 5, 8 meters?
Yes, several meters, 5 or 8 meters.
Yeah. Unbelievable. The vacuum vessel sector we see in place here is also due to be removed for repairs. We've got a few minutes now. We've been filming for 2 days. I worry that we haven't conveyed the scale of this operation, of what's going on here. People from 35 different countries, motivated by knowledge, expertise, but also just dedication to a cause. It's the level of work that's done here, the scale of it, it's absolutely mind-blowing.
I've worked in a lot of different fields, a lot of different locations. This is the first one where every morning as I drive to work, I think about my daughter and future generations, because we're building something that could really change the future, could make a complete difference for that future generation.
What will the world be like when we have working fusion power plants?
You can imagine, okay, we will have endless energy, could replace the oil. It will, for sure, change our life, change the world a lot. I always talk with my friend or my colleagues.
Yes.
Okay, we are working on this project. It's like when people, human, learn how to use fire.
Yes.
This is the second fire of the human in our history.